All right, welcome back. Dr. P here, and in today's lecture, we're going to take a look at the mole. This little guy who was visiting us before, and actually, no, it's not a small subterranean mammal that we're talking about, but rather we're talking about a um, SI unit of amount called the mole. So let me zoom in a little bit here so that we can go ahead and work on some notes. So I want to talk about a few things today, namely atomic masses, and also the mole. And we'll also talk about molar mass, I believe, as well. And then in subsequent lectures, we'll go ahead and look at percent composition of compounds and how to determine the formula of a compound. And then we'll get into chemical equations and balancing chemical equations. And ultimately, we'll transition our way into stoichiometry, doing calculations involving different amounts of reactants and products. Let's go ahead and look at atomic masses first. So carbon, carbon, specifically C12, is the standard. And it is assigned a mass of 12 AMU, which is atomic mass units. And you can measure the mass of individual atoms, well, the average mass of atoms, by you can measure the mass of a collection of atoms, essentially one at a time, using something called a mass spectrometer. It would help if I could spell. And the text does talk about the mass spectrometer, and I'll let you read up on that. I'm not going to hold you responsible for how it works, but if you are interested, it's kind of cool technology. Now, the carbon atomic mass, or atomic weight, is reported as 12.01. Question is why? Well, it's because naturally occurring carbon is a mixture of carbon 12 and carbon 13 and tiny amounts of carbon 14. So thus, the atomic mass that's listed on your periodic table is a weighted average of your various isotope masses. We talked about isotopes last time. But for stoichiometric purposes, for doing calculations, when we run chemical reactions on a macroscopic scale, we can just use the average. So we can use 12.01. Now, mass spec can also be used to determine relative amounts of isotopes of an element. So using mass spec, we would see that the ratio of naturally occurring carbon 12 to carbon 13 is about 100 to 1. And then it's something like, I don't know, 10,000 to 100,000 to 1, carbon-12 to carbon-14. There's not much carbon-14. All right. Now the other thing I wanted to talk about today, the other main thing I wanted to talk about today was the mole, which is not a small subterranean mammal, no matter how much it may think otherwise. But rather the mole is, well, it's sort of like a dozen, only much, 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 much larger. I sometimes call it the chemist's dozen. Put that in quotation marks. You know how a baker's dozen is 13 of something, because the bakers give you one extra if you order a dozen. Well, a chemist's dozen is a whole bunch. So, 1 mole, the abbreviation is MOL, I know, not much of an abbreviation, is 6.022140076 times 10 to the 23rd of something. Okay, so that is a mole. Now, this is the current definition. As of 2019. The old definition, which I'm telling you about the old definition because it actually is important for the way that chemists think about and used to think about and still think about doing calculations and working with, you know, these large quantities of really tiny molecules. So 1 mole is equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. Okay, now for our purposes, we'll go ahead and, you know, for most of the time we can just cut off Avogadro's number there, since we're usually not going to have things with more than 4 sig figs that we need to worry about. But yeah, in 2019 the definition was changed. Okay, so that instead of it being an empirical definition, where a mole is the number of carbon atoms in exactly 12 grams of pure carbon-12. So this makes 2 assumptions. One, you can measure exactly 12 grams, which is really difficult to experimentally measure an exact amount of something, and that you had pure carbon-12. That's also sometimes tricky to get a pure sample of just one isotope. It can be done. You can use mass spectrometry to do it, actually. Measuring the exactly 12 grams is the tricky part. Instead, a much easier definition simply defines the unit in terms of Avogadro's number. So now a sample of an element with a mass equal to its atomic mass in grams contains 1 mole of atoms. So we can then say our atomic mass is mass in grams of 1 mole of atoms of that element. So if we see that chlorine has an atomic mass of 35.45, then we know that if we have a sample of chlorine and we have 1 mole of sample, we will have 35.45 grams of chlorine per mole of chlorine. So usually we report these in units of grams per mole. So that's going to be our standard unit for representing molar masses, or sorry, atomic masses. Molar mass is the same thing but for molecules or compounds. So for the molar mass, we can add up the atomic masses of all the atoms. So we'll call those constituent atoms. And then the molar mass is also, we'll say it equals mass in grams of 1 mole of the compound. And then it's also known as, aka, also known as molecular weight. Mole weight. All right. So that is the mole and molar mass. And I think this is one of the key concepts in chemistry is the mole. Yes, this little guy. Okay, you can leave now. Yes, you can leave now. Yes. Anyway, so I know this is kind of a short video, but I really just wanted to introduce the mole and sort of what it means, because when we start doing calculations, we'll be using grams per mole, or maybe we'll be using moles per liter. And we'll see that when we do calculations, we want to actually convert all of our units into moles to do the actual calculation. And we'll talk about that a little bit later on in these chapters. All right. Well, until next time, stay safe out there. Bye now.